name is Takei, and I'm going to be talking about macroscopic Josephson devices and magnetic nanostructures. And I think throughout this conference, we've heard talks about where conduction electrons coexist with classical magnetic order parameter and how spin-orbit interactions can give rise to sort of coupling between these two things. So this talk is going to be based on that kind of physics, spin transfer torques and spin-orbit torques, but sort of extending from that. So just to start off, the type of system that I'm going to start off with is this kind of bilayer system. Let's say you have a normal metal here, which can harness a charge current, and it's attached to, let's say, an insulating magnetic system with long-range magnetic order. And we know that spin-orbit interactions in this kind of heterostructure can give rise to magnetoelectric coupling between the charge current and the magnetization. And in particular, the charge current can induce torques on the magnetization, and there's sort of a reciprocal effect in which magnetization dynamics can induce electromotive forces in the adjacent normal metal. So this kind of phenomena is very well observed in experiments as well, and this was covered a lot during the tutorial last weekend, as well as a number of talks during the conference. So one facet of this problem is spin transfer torques. A very simple picture for that is that you have a charge current, let's say, going through a normal metal, and by direct spin Hall effect, if there's spin-orbit interactions inside a normal metal, direct spin Hall effect gives rise to a transverse spin current. And if that polarization of that spin current is non-collinear with the magnetization, then that can, the transverse component can be absorbed by the magnetization and induce a torque. And there's sort of a related phenomenon to that, inverse spin galvanic effect, which is a non-equilibrium effect in which if you pass a charge current through a metal, that induces a non-equilibrium spin accumulation, and that spin accumulation can exchange coupled to the magnetization and also induce a torque. And then there's sort of an inverse phenomenon, which people often call spin pumping inverse spin Hall effect. And in this kind of experiment, the charge current is not excited, but instead you use magnetic resonance to excite the magnet. And if the ferromagnet then undergoes magnetic precession, then the dynamic magnetization can then pump spin current into the adjacent normal metal, and the spin-orbit coupling inside the normal metal can give rise to transverse charge current, which can be detected as a voltage drop across the normal metal. So there's a lot of work done to try to understand the microscopics behind all this phenomena, and this was covered a lot during the conference. In this talk, the way that I want to, one way to sort of view this is to consider this kind of bilayer system again and try to figure out what kind of torques can arise just based on symmetry arguments. So imagine that you have this bilayer system again. You have a normal metal, this gray region, and a magnetic insulator. And if you assume structural invergent asymmetry in the growth direction, which I take to be the z-axis, and if there's continuous rotational symmetry about the z-axis, and mirror symmetry for all planes perpendicular to the xy plane, then you can write down quite generally the type of torques that can arise. And this is what Hiro Sonoba in his tutorial talk wrote down a couple of torque terms. The first term, which is proportional to theta prime, is what he called the non-dissipative or the field-like torque. And then there's another term which is proportional to theta, which is what he called the dissipative or the damping-like torques. And within your response, then you get for free that from Onsager reciprocity that if these kind of torques are there, then Onsager reciprocity gives you that magnetic dynamics should give rise to electromotive forces in the adjacent normal metal. And this electromotive force, I call this epsilon here, has a couple of terms again, which are proportional to theta prime and theta. And both of these parameters enter sort of symmetrically governed by Onsager reciprocity. So the question that I'd like to address in this talk is, what if now we look at this bilayer system and start lowering the temperature? And then one might expect this kind of magnetic system, magnetization, may start to inherit some quantum properties. And this is going to be macroscopic quantum phenomena. Macroscopic because this magnetization is basically treated as some macroscopic variable which collectively describes many microscopic spins inside this magnet. So I want to look at a problem where this collective degrees of freedom start to inherit some quantum properties as we lower the temperature. And because we have this sort of magnetoelectric coupling of that variable to the charge current, it might give us a handle on manipulating this macroscopic quantum variable using the charge current. And the particular device that so the macroscopic quantum tunneling, actually, I should say, in magnets has been studied a lot. This is not a sort of a new concept. It's been studied starting in the 70s and 80s and 90s. There's a lot of work done in trying to see manifestations of macroscopic quantum phenomena in magnets. One particular problem people studied was depending of domain walls, how quantum mechanics plays a role there. Also, tunneling of a monodomain magnetic nanoparticle like ferromagnet or antiferromagnetic nanoparticle, and seeing how the order parameter tunnels, quantum mechanically tunnels between two different classically stable configurations. But as far as I know, this area sort of in the recent years sort of died down because there's no real clear signature of macroscopic quantum phenomena in these systems. But I would like to sort of revisit, I'd like to motivate revisiting this problem again in the context of these kind of bilayer systems. Now in spintronics, there's been a lot of activity, as I sort of pointed out in the beginning, over the last 10 years, trying to use electrical signals to control magnetization. So why don't we try to revisit this problem and try to make sort of interesting quantum devices out of this kind of bilayer system. So I want to propose a couple of concrete examples of how this phenomenon may be detected. And so I'm going to propose a couple of macroscopic magnetic qubits. And this qubit can be controlled, manipulated, and read out using spin Hall phenomena. Exactly the type of setup that has been studied a lot in spintronics over the last decade or so. So this kind of device should be possible with the current spintronics technology. It should offer a good qubit coupling as well as scalability. And this is an example of a macroscopic qubit. And the only macroscopic qubit we know today is superconducting Josephson qubits. So this would be sort of a second proposal for a macroscopic quantum bit. So I want to sort of talk about what kind of energy scales what kind of temperatures we need to lower so that we can operate these devices in the quantum regime and give estimates for decoherence times and so on. Okay, so I'm going to give a couple of prototypes, ferromagnetic as well as an antiferromagnetic prototype. And I'm going to show how these qubits can be fully controlled using spin Hall phenomena. Okay, so first starting off with a ferromagnetic prototype. So the type of system I want to consider is that I have a monodomain ferromagnet in the middle, which is coupled to this normal metal on the left side. And it's exchange coupled to a fixed ferromagnet, which is fixed in the x direction. And I'm going to assume that there is an easy plane anisotropy in the central magnet, so I can write down quite a simple Hamiltonian for this magnet here. So we have exchange coupling of this magnet to the neighboring fixed ferromagnet. So that coupling is J, what I call J. That's the inter-ferromagnet coupling. And then I have an anisotropy K, which basically is an easy plane anisotropy. And then I'm going to couple that to a normal metal, and this normal metal may have a strong spin-orbit coupling. Typically what's used in spintronics is platinum and tantalum. I'm going to consider that kind of metal in this region as well. And I'm just going to simply assume that that metal is just a standard metal that obeys Ohm's law. And through this spin transfer torque type physics, there could be coupling of the electrical current to the monodomain magnet. So I'm going to induce torque term, which is the spin transfer torque term that might be generated due to the charge current. And then I'm going to also consider enhanced damping of the magnet within this ferromagnet due to its coupling to the neighboring normal metal. So that's this second term here. And due to Onsager reciprocity, this torque term is going to give rise to electromotive force due to the dynamics of this magnetization. And this electromotive force can be written in this form, which is precisely Onsager reciprocal to this torque term here. So the Landau-Lifshitz-Gilbert dynamics for this ferromagnet in the middle can be written in this form. This alpha here is the intrinsic Gilbert damping inside the ferromagnet. This is the enhanced damping due to the coupling to the normal metal. And there's also sort of intrinsic Gilbert damping inside the ferromagnet. And I'm going to add the transfer of spin across this interface as a torque term. So this torque term is going to enter that. So the dynamics could be written in this form. Okay, so now I want to consider the limit where the easy plane anisotropy is much stronger than the inter-ferromagnet coupling J. So then in that case I can parameterize the macro spin in the ferromagnet in terms of two variables, bar phi here, which is the azimuth angle of the macro spin within the easy plane, and the z component of that spin, which it cancels out of the xy plane. Then if you write the classical dynamics, magnetization dynamics in terms of those two variables, then it reduces to these two equations in the limit of strong anisotropy. And the charge current actually enters here. So J is proportional to charge current in the normal metal. And then we have enhanced Gilbert damping that enters both of these two equations. Now, if we ignore Gilbert damping for the moment, these two equations, if we notice that as z and phi are conjugate variables, these two equations are Hamilton equations for an effective Hamiltonian, classical Hamiltonian, which has this form here. And so this is the usual kinetic energy term. This is just a particle that's moving in a potential that's defined by this potential here, which is a washboard potential. But the washboard tilt is actually provided by the charge current, the external charge current. This eta parameter here is given by this ratio, dimensionless parameter. In this dimensionless parameter, the charge current actually enters there. So the tilt of the washboard potential is provided by the external charge current. And if we want to go into the so-called phase regime, where phase is the well-defined quantum variable, then we want this so-called Josephson term to dominate over the charging term. And so that means that we want to be in this regime if we want the phase to be sort of the well-defined quantum variable. So we assume that k over j, because we're in this limit of strong anisotropy, is much greater than 1. But to be in the phase regime, we want the k over j to be still much less than the total magnitude of the spin inside the ferromagnet squared. So we want to be sort of in this sweet spot here so that we can operate our quantum device within the phase regime. All right, so now if we look at the washboard potential, we want to now operate in a regime where this eta parameter, which was this charge current, if I go back to this eta parameter here, which is proportional to the charge current, we want to be operating where eta is sort of close to 1, but slightly less. In that case, the washboard potential is sufficiently tilted, and we can find the plasma scale for this oscillation, harmonic oscillation, within one of the minima. And that plasma frequency scale is actually set by geometric average of the anisotropy energy scale times the exchange coupling to the fixed ferromagnet, K times J. And the energy barrier is set by the exchange coupling to the fixed ferromagnet. And if we lower the temperature low enough such that we're in a temperature below this value, below the plasma scale, then the quantization of energy levels within each of these minima become important. and we may use these lowest two states as our basis for our qubit. And the nonlinearity is actually provided by this Washburn potential. We can actually model the nonlinearity and show that these two levels, the 1 and 2 levels, are off resonant with the first two levels. So the qubit can actually be controlled by adding a small AC component to the charge current. So if we add an AC component which has the same frequency as the lowest energy splitting, then you can write down within rotating wave approximation the two-level effective Hamiltonian for this qubit. And so that generates this transition between the 0 and 1 state. And the Rabi frequency is actually set by this AC component of the spin current. So that's basically the spin current, AC spin current that's passing between the normal metal and the magnet. And that AC component sets the Rabi frequency scale, the amplitude of that. And that's multiplied by this prefactor. This prefactor is actually quite small. K over Js squared is the parameter that we assume to be small within the phase regime. But that's taken to the 4th root, so that number could be of order 1. So now, this qubit can be read out if we increase the charge current inside the normal metal. So we tilt the Washburn potential further and further, so that so if we bring the charge current larger and larger, so this ratio here reaches 1, then the upper state, you're essentially left with two states inside that local minimum, and the upper state is going to have exponentially more likely to tunnel out of this of that minimum, and that's how you can read out the 1 state. And what that classically means is that the particle tunnels out of this minimum and it just falls down this Washburn potential. And this classically means that this magnetization is going to start dynamically precessing. Once it starts tunneling out, it's just going to start to rotate. And that's going to induce electromotive force inside the adjacent normal metal. So this is how one can read it out. And you could estimate how much this precession frequency is going to be. If we model, so this particle is basically a particle falling down a hill, and that this particle is going to reach some terminal velocity, which is defined by Gilbert damping. So we can estimate how fast this ball is going to fall down this hill. And so if we find that terminal velocity, then you can find how much electromotive force is induced inside this normal metal, and one can estimate how big of a voltage one needs to measure so that, in order to measure this 1 state after it tunneled up. Now, I want to also discuss a bit about decoherence, and what I'm going to consider here is the effect of the Gilbert damping inside the ferromagnet feels. So the ferromagnet has both intrinsic Gilbert damping as well as damping due to the coupling to the electron continuum in the normal metal. So there's some damping alpha tilde which includes both of those effects, and by fluctuation dissipation theorem that should give rise to a couple of Langevin fields, stochastic fields. And one notes here that this is the fluctuations that causes the magnetization sort of fluctuate in the z direction, while this field corresponds to sort of fluctuations that give rise to fluctuations within the xy plane. And due to the strong easy plane anisotropy, this noise term actually is strongly suppressed than this term, which gives rise to fluctuations within the U1 plane. So we're just going to consider the noise due to this field here, and by fluctuation dissipation theorem, the symmetrized noise correlator for this field is given here. And that if you project this dynamics down to the effective 2-level Hamiltonian, it gives rise to a stochastic sigma x term, the noise in the sigma x. And the coefficient has a noise correlator of this form here. So then the gamma 1 time, the sigma x, is going to give rise to longitudinal relaxation rate which is proportional to the noise correlator here, evaluated at the transition frequency, omega 1, 0. And that longitudinal relaxation rate is actually given by alpha, the Gilbert damping, times the anisotropy energy scale, K. So that sets the gamma 1. Okay, so now I want to also propose an antiferromagnetic prototype. This is very much an analogy with the ferromagnetic one. So, so what I'm going to assume here is that we have a very simple monodomain Heisenberg antiferromagnet subjected to a magnetic field in the negative z direction. And so we can write down classical Lagrangian for this antiferromagnet here. And chi here is the perpendicular susceptibility. It's the susceptibility for magnetic field applied normal to the Néel vector. And then we have a term proportional to the magnetic field. And we're just going to assume that this Néel vector is exchange coupled to the ferromagnet in the x direction. So this is the exchange coupling between the antiferromagnet Néel vector and the ferromagnetic moment fixed in the x direction. And again, normal metal has the usual Ohm's law. And again, so this normal, the current inside the normal metal can couple to the Néel vector, giving rise to a spin transfer torque-like term acting on the Néel vector. And the dynamic Néel vector can also pump spin current out into the external normal metal. And that's the enhanced Gilbert damping due to the coupling to the normal metal. And by Onsager reciprocity, this kind of torque term is going to give rise to electromotive force in the adjacent normal metal. Okay, so then one can write basically Euler-Lagrange equation corresponding to this Lagrangian for the total magnetization, the total spin in the antiferromagnet, which is m. That's the total spin inside this. It's a macroscopic variable. And this is the unit vector. N is the unit vector pointing parallel to the local to the Néel vector. Okay, so the dynamics can be written in this form, and the torque enters the dynamic equation for the total spin. So if we now consider magnetic dynamics, so the antiferromagnet has two Goldstone modes, but the magnetic field is going to gap out one of those Goldstone modes. And so we're going to project the dynamics to the gapless sector of those two Goldstone modes. So we want to consider the rotation of Néel vector within the xy plane, as well as small fluctuations of the total spin in the z direction. And so the Néel vector can be parameterized in terms of azimuth angle within the xy plane. And then the total spin may have an equilibrium value, which is basically the canting due to the magnetic field, plus small non-equilibrium fluctuations above that equilibrium value. And so if we rewrite the antiferromagnetic LLG dynamics in terms of these two variables, phi and c, then it reduces to these two equations. And the J, the external charge current, actually enters here, and there's enhanced Gilbert damping. And the effective, if we now notice again that C and phi are conjugate variables, then the effective Hamiltonian, which gives rise to this dynamics, Hamilton dynamics, is this Hamiltonian, which looks pretty much the same as the ferromagnetic case. Again, the tilt of the washboard potential is provided by the charge current. And if we want to be in the phase regime, then we want this J to be much less, J times chi to be much less than, much greater than 1. And J times chi is estimated to be J, the exchange coupling to the ferromagnet, over the internal exchange scale of the antiferromagnet, which could be very small, but that's multiplied by the total number of spins N inside, on one of the sublattices on the antiferromagnet. So this parameter hopefully is large. If you can make a large enough sort of monodomain antiferromagnet, maybe we can go into this regime where this is much greater than 1. Okay. So again, we want to be operating our quantum device where the washboard potential is sufficiently tilted, and so that's the regime where eta is close to 1. And in that regime, the plasma frequency scale in this case is actually given by J over chi, square root. So that's the energy scale which sets the energy splitting of this device. And the barrier is set by the exchange coupling to the ferromagnet. And again, we want to be operating at temperatures much below than this plasma energy scale, so that the energy levels, we're basically operating within the lowest two energy levels here. Again, so we can add AC component to that charge current at the frequency which is in resonance with the lowest two energy levels, and that's going to give rise to transition between the 0 and 1 states. And the Rabi frequency is again set by the amplitude of the AC part of the spin current that's being transferred across the interface, and that's multiplied by this factor 1 over j pi to the 4th root. This number can be pretty big. That's our assumption to be in the phase regime, but we're taking this to the 4th root, so hopefully this number is of order 1, and so Rabi frequency is sufficiently high. Okay, so again, particle rolls down once we tilt the potential steep enough, and that, to read it out, that means that this nail vector is going to start precessing. As it rolls down that hill, that physically means that this nail vector is actually rotating within this xy plane, and that's going to give rise to a motive force, and that's how one can read it out. And again, putting in the Gilbert damping and finding the terminal velocity for that particle to fall down that hill, you can calculate how big of a motive force you need to measure in order to read out this device. And now to the coherence in this case, we're going to add again two Langevin fields which couple to the two conjugate variables. And this Langevin field has this correlator which is governed by fluctuation dissipation theorem. And in this case, the fluctuations of the magnetization, the total spin, basically the fluctuations of the spins that sort of fluctuate in this direction is strongly suppressed by Néel exchange scale, the internal exchange scale of the antiferromagnet. So this noise contribution turned out to be much smaller than this term, which is basically fluctuations, noise that rotates the Néel vector within the xy plane. So we're going to again consider the noise due to this field here, and that field, this Langevin field, if we project it to this effective two-level Hamiltonian, again gives rise to a sigma x type noise, where this correlator, a correlator for this stochastic field, has this frequency spectrum. And so the longitudinal relaxation rate, if we just use Fermi-Golden rule again to calculate this, then that gives you gamma 1 rate, which is proportional to this noise spectrum evaluated at omega 10, the transition frequency of the lowest two states. And in the case of antiferromagnet, the gamma 1 turns out to be very fast. So it's Gilbert damping times the internal exchange scale of the antiferromagnet. So it's very much stronger, larger than the ferromagnetic case. Okay, so just to quickly summarize, so we consider a couple of prototypes. Qubit variables here are the azimuth angle of the macro spin and also the z component of the spin. The antiferromagnetic case is the azimuth angle and the total spin in the z direction. So the temperatures that you want to operate at are going to be you want to be, in the ferromagnetic case, you want to be lower than this product of the exchange coupling between these two ferromagnet times the anisotropy scale square root. For the antiferromagnet, it's this exchange scale times the internal antiferromagnetic exchange scale square root. And so the gamma 1s are given here. Now, I just want to say a few things about how to couple these devices. And one way to do it for this ferromagnetic case is now we have this device, we can actually stack them up in a, let's say, a vertical direction, so that you have a normal metal on top of this, and then the same ferromagnet, another one on top of this, and another fixed ferromagnet on top. And you can exchange couple. Let's say the simplest model maybe to couple this is to couple these two ferromagnets, the adjacent ones, through exchange interaction. And if we assume again that the anisotropy scale is much larger than this interferromagnet exchange, which I call J prime, then the simple classical Hamiltonian for this exchange is just given by J prime times S cosine of the difference of the angle, azimuth angle. And if we project now to down to this four-dimensional Hilbert space that's defined by the Hilbert space of one qubit and the other two qubits, then it gives rise to a sigma x type coupling between these two devices. And the coupling scale is J prime times this constant, but if the scale of this coupling is actually the ratio of J prime, which is the interferromagnetic coupling J prime, over the exchange coupling in this direction times this plasma frequency scale for this single qubit. So that's the scale of the coupling between the two qubits. And so one way, you can make a very fancy lattice of this thing. So I'm just tilting this in the vertical direction. I'm kind of tilting this way. Now the normal metals on top, I have this ferromagnet of interest in the middle, and then we have the fixed ferromagnet on the bottom. And then you can couple all of these in kind of a two-dimensional array like this. And you can actually tune the qubit on and off by, first you can turn it off if you tune the omega 1, 0, so the lowest energy, the splitting of the two lowest energies for each of these qubits. If you tune them to be different values, and then if that difference is much larger than the interqubit coupling, then you can tune the coupling off, and you can tune the coupling on by bringing them resonant with each other. Okay, so in principle, these things can be done theoretically. Okay, so you can make a sort of a device out of this kind of quantum devices. Okay, so now I want to give some numbers for the sort of state-of-the-art spintronics devices that people can make in a lab now. So I'm going to consider a YIG platinum bilayer. Let's say I take that kind of system, and I'm going to model this YIG as a cubic ferromagnet with lattice constant 12 angstroms and total spin 14.2. And I'm going to consider a slab of 1 micron by 1 micron by 100 nanometers for this thing here. And then I'm going to assume that the easy plane anisotropy is going to come fully from this shape anisotropy. Then if I assume that, then the anisotropy scale, if I just assume it comes from shape, then that's of order 300 millikelvin. And so if I multiply that to, let's say this exchange coupling between these two ferromagnets is 1/10 of that, 1/10 of this scale, then the temperature that we want to operate, the upper bound for the temperature for operation is around 100 millikelvin. Now, told Gilbert damping, I'm being a bit optimistic, but let's say alpha is 10 to the minus 5, we can make that somehow. Then T1 time is going to be order 10 microseconds. Because the T1 time is basically given by this scale here. We know K from this energy scale for K is given here, alpha is given here, and putting those in, T1 time is about 10 microseconds. Now if we assume, now we want to see how big of a charge current we need to bring it into this nonlinear regime. So we want to sufficiently tilt the washboard potential. So if we want to sufficiently tilt it, we got to figure out how much charge current we need to pass through the normal metal. And the estimate for that, if we use a spin Hall angle, which is quite often reported, a large value, let's say 10%, and if the thickness of this normal metal, T sub n, is 10 nanometers or so, then the charge current density you need, linear charge current density you need, is about 10 to the 6 amps per meter. That's kind of big. So maybe this might be a bit of a problem, but let's see. And then let's say we assume that exchange coupling, the inter-exchange coupling here is same order as the exchange coupling between this ferromagnet and the neighboring one, so J is equal to J prime, let's say they're about the same order. Then the 2 qubit time over T1 is about 10 to the minus 4. So that's, this ratio is basically telling us within this coherence time, how many qubit operations can we do? And it's about 10 to the 4. So it might be okay to we can get about 10 to the 4 operations done within this time. All right, so now for the antiferromagnet. I'm going to consider potassium nickel fluoride platinum type bilayer, let's say. So potassium nickel fluoride is a cubic perovskite material, and lattice constant is about 4 angstroms. Total spin on each site is about 1, and the internal antiferromagnetic exchange scale is about 0.01 eV. So with that scale, I'm going to consider, so let's look at the upper bound for the temperature. So the exchange scale, let's say here, using a typical value that people report for exchange bias, for example, between an antiferromagnet and a ferromagnet, people may report about 100 millitesla. So if I use that value for this exchange scale between the antiferromagnet and the ferromagnet, and putting this exchange scale inside here, that brings us up to about 3 Kelvin. So the upper bound for quantum operation is around 3 Kelvin. It's a bit order of magnitude higher than the ferromagnetic case. But if we now look at T1 time, which is inverse of h bar over Gilbert damping times this exchange scale, the exchange scale of the antiferromagnet is pretty big. That brings us down, way down to about 10 nanoseconds, T1 time. So that's kind of short. Now, if we look at how much charge current we need to pass through this normal metal so that we can go into this nonlinear regime, so again, using spin Hall angle for this antiferromagnet normal metal interface of 0.1, and then thickness of normal metals, let's say 10 nanometers, then we need a charge current density, linear charge current density of about 3 times 10 to the 5 amps per meter, which is also kind of big. And then if we again assume, I didn't write it here, but if we again assume that if we are able to couple this kind of qubit device and assume that there's some coupling between the nail vector, exchange coupling between nail vector in this vertical direction, which is of same order as this exchange coupling between the nail vector and the ferromagnet, then again, the 2 qubit time ratio to T1 is going to be about 10 to the 4. So 5 minutes? Okay, yeah, I'm basically done. Okay, so these are sort of the numerical estimates. So just to summarize, so basically it gave a couple of proposals for a quantum device that makes use of spin Hall phenomena in spintronics. And I tried to give some estimates. So I gave a couple of prototypes, a ferromagnetic one and an antiferromagnetic one. And so these are sort of the upper bound for temperature estimates based on sort of what kind of materials people are using in spintronics today and the type of temperatures that we need to operate these devices and T1 times and so on. Okay, so thank you very much, and I'll take some questions.
So when you introduced your prototypes of ferromagnetic and antiferromagnetic qubit, we can see that there is a different height in your samples, and is there any physics standing behind difference in the height of these qubits, or this is just a picture?
Well, there is kind of a reason why I drew it that way. So in this case, the easy plane anisotropy kind of plays a role. So we want the magnetization to be sort of confined to some XY plane. So since I assumed that anisotropy, that energy scale for the order parameter to be in that plane is coming from shape anisotropy, I wanted this to have sort of a film geometry. In this case, the energy scale to keep this nail vector within the XY plane is not coming from shape anisotropy, but it's actually coming from the magnetic field, the Zeeman effect. So in this case, the shape may not be so crucial. The anisotropy is not, that scale is not coming from shape anisotropy, so it's not so crucial. So I kind of drew a digger there.
Thank you.
More questions, please?
Yes, and when you talk about two ferromagnetic qubits, you do not also include in your system dipole-dipole interaction. So you suppose that it's quite small?
No, I mean that's definitely will play probably a big role in this kind of device, and I did not take that into account in this calculation. I think it might be detrimental. I don't know. So that's why I propose this antiferromagnetic one as well, because the antiferromagnetic one, the dipole effect should be more or less absent. So maybe going to antiferromagnet will be crucial, because this kind of device, you know, dipole effects will kill all this.
Yeah,
it will kill all this physics. Yeah.
Also the same mention also. In fact, in the ferromagnetic sample, you have not, in the case of you know cubical, you have not uniform state, but some quasi-uniform state, Leaf state, and the dynamics of it could be not, you know, the simple microspin and so on.
Right. So you're talking about non-uniformities in the magnetization.
Yeah. Right. In the angles.
Yeah. No, absolutely. So we will definitely have to avoid those kind of things. But I think people do, if they make it small enough, they can make like a pretty, you know, uniform macros.
Yeah, but you know, it's very the magnetic dots and here what is the magnetization there? It's many. It depends on this, its sizes, geometric and so on.
Absolutely, yeah. So yeah, that
and exchange events, yeah. Okay, thank you.
You talked about some states that are confined in the washboard potential, right? Yeah. And your ferromagnet starts to precess only when those particles escape from the well. So my question is where those states are in space. So they're confined and where they are.
Well, okay, so if it's confined to one of those potential wells, like one of those wells in the washboard potential, classically that means that the expectation value of phi is pretty much fixed. It's not moving, as long as it's operating within one of those wells. So physically, if you just view it, if you view that macro spin, it's probably the angle is just fixed to some location, but it's basically transitioning between zero state and one like sort of excited state within that sort of well, right? And then when it tunnels out, classically it means that this thing starts to rotate. As the ball sort of runs down the hill, that means that there's an expectation value for phi dot. That thing is going to now start, you know, precessing. The phi is going to have some sort of velocity, so to speak. It's gonna,
I see. Thank you.
If I understand correctly, this device is always operating with a drive current, which is a significant current. And I'm just worried a little bit about effects of fluctuations in this drive current. How accurately do you have to control the drive current in order to stay in the regime where you can do all these measurements?
Right. So yes, so fluctuations in the current can give rise to an extra source of noise on the device as well, which may give rise to extra decoherence. I didn't consider that yet. I did think about it, but I didn't explicitly calculate how big that effect is, how big that effect is compared to, let's say, Gilbert damping that's intrinsic in the magnets and coupling to the electron continuum. I haven't done that calculation, but I think that's an important thing to do also. What's the effect of fluctuations in the current?
One more question. Could you show your effective Hamiltonian for the ferromagnetic sample?
So, for example,
but effective Hamiltonian or on phi, yeah. Here, in your case, the phi is small, so the switching of phi is quite small, so it's because it's strange that phi is just not the sign of phi, but phi in your Hamiltonian. For example, because if it rotates on the, for example, 6 pi, then it's grows.
This term here.
Yeah. So you mean that phi is very small, yeah? Or so it's...
No, this is not... phi can take any value. So this is what gives the Washburn potential, which is in principle unbounded on both sides, right? If you take phi to minus infinity or plus infinity, the Washburn potential is basically like, unbounded. So this is what gives the tilt for that Washburn potential.
Yeah, but it's strange. Okay, thank you.
In this geometry, you have electric current which has a very large current density and which is situated very close to magnetic particle. Produce some external magnetic field in addition to ones which are present. Is this effect calculated in Hamiltonian, and is it noticeable?
Yeah, that's a good question. Orsett fields definitely will be there. I did not include that in my Hamiltonian. I did not estimate how big that effect is.
What is the quality factor would be for your system? Because you have an oscillating component of AC current and you will have oscillating magnetic field. How this oscillating field will excite the state directly?
I don't know. I have to think about how that AC field that's created by the current is going to affect. I don't know an answer off the top of my head.
Thank you.
Yeah.
So just to add to Bert's question, about the oscillations of the electrical current, which is probably a very serious issue in practice. The thermal fluctuations are implicitly included in the theory because the Gilbert damping is not just the Gilbert damping of the bulk, but also whatever Gilbert damping that arises from the spin pumping and the interplay of the spin pumping with the spin Hall physics. So what's not included are the additional possible oscillations, due to whatever else you might be having in the circuit. And I guess it's not so much a question to the theorists. I don't know even how you would be able to include it in the theory. The shot noise is probably not that important. The thermal oscillations are already there. What's not included are some, electronic stuff that is really beyond any kind of modeling.
Yeah, there might be more.
But it could be very important in practice. But that's, I guess, more like a fun engineering question kind of thing.
I have two questions. First, can you dynamically change Rashba potential of your qubit?
The Washburn potential dynamically change. Yeah. Yes. So by changing the current, the external current in the normal metal, that's going to change the tilt of this. So if you have some sort of time-dependent DC, not DC in that sense, but if you have a way to tune the tilt, you can do that with the charge current.
Okay. Yeah. And one more. As you say, during readout, the particle tunneling out from a potential well. And that means that the readout procedure destroys the initial state of your qubit.
Right. So once the particle tunnels out, you basically are at the end of your computation, and you basically read out if it's in a one state or not. Essentially, so you destroy the quantum superposition.
And how to regenerate memory of this qubit? You read out and
that's it. Yeah, that's it.
So I think you must consider this problem for this qubit.
But typically, I don't want to make overarching statements, but eventually, if you want to make a quantum computer or something out of this, typically you initialize your states, and then you unitarily evolve that system, which is the computational process. And then at the end, you get an answer, and then you read it out. That could be one useful way to use this device. That you can do in principle if you can make a device with this kind of thing. Right? Once you have your answer, which is in some sort of state, you can read out each one. And
So you
still-
mustn't save the qubit state after readout.
Sorry?
So you mustn't save qubit state after readout.
Yeah. Yeah, maybe, yeah.
Okay, thank you.